Okay, I have a couple more notes for you for 13.2 before we go into 13.3. First thing is, I made a mistake in the last video. I changed it with some editing, but there was a K there. I forgot when I subtracted to have the K, so this answer is changed a little bit. Where we picked up from, I'll pick up from last time. We finished with this. I had something, a spring. Its relaxed length is just that length. I called the stretch E for the equilibrium position. I'm going to call it something a little bit different this time. I'm going to call it delta L. So the length of the spring is L. Its change in length is delta L when you hang a mass on it, such that when you hang the mass, it just hangs from the spring. The force of the spring up is equal to the force of gravity down. And then when we pulled it down a little bit, we let go, it shoots back up. And I said yesterday that if you looked at this math looked exactly like the math we had for the spring that was going back and forth on a horizontal surface that was frictionless. We had 1/2 Ka squared equals 1/2 mv squared, and I was trying to say to you, well, we get the same thing here. So it actually oscillates just like a horizontal spring or a mass on a horizontal surface going back and forth like this. I'm going to prove it to you a little bit more thoroughly here. So this really, I just took this equation here and I just replaced E. Now I'm going to call it delta L, the change in length of the spring when it's at its equilibrium position, not the relaxed length of the spring, but the equilibrium position for the mass and spring system where the force up equals the gravity down. And this is all the same math that is just right here. It's the same math here as here. It's just delta L instead of E. And then let's work on this side. So this time what I'm going to do is I'm going to let it go and have it come up some distance delta x, and we're going to see that this delta x up above the equilibrium position is the same as this A down, but I'm going to prove it to you. Okay, so this change in length of the spring initially is delta L plus A. That's how far down it is. So 1/2 K. Instead of writing delta L plus A, I wrote A plus delta L. Doesn't matter. Square it. It's the same math as this up here. And then now the spring is not stretched quite so much. It wants to be at relaxed length L. And when I took delta L minus delta X is going to be the change in length of the spring, how much it's stretched. And then we also have gravitational potential energy of mg delta x. I'm going to work on this side over here, 1/2 K delta L squared, and that is going to cancel with this 1/2 K delta L squared. I should have, so that one's now gone. Minus 2, but there's a half, so minus K delta L delta X plus, so minus X times delta X times delta X, even though it's negative, is delta X squared, so plus 1/2 K delta X squared, and I still have this plus mg delta X, and I canceled out this one with that one, so now these are gone, so I have minus K delta L plus 1/2 K delta X squared plus mg delta X. But the same thing we did the other day over here where we said K times delta L. Well, K times delta L is where, at this position, that's where the spring force equals the force of gravity. So the spring force equals the force of gravity, and K delta X, but my delta X is delta L when the forces are equal. K delta L equals mg. And so we said K delta L right there is mg. So plus mga minus mga equals 0. We're going to be able to do the same thing over here, it turns out. Oh, I forgot the, man, so many mistakes, huh? So this is delta L delta X. K minus K delta L delta X. But minus KL is, or K times delta L is mg. So minus mg delta X plus 1/2 K delta X squared plus mg delta X. And we've got a minus mg delta X, a plus mg delta X, goes away. And the only thing we have left over here is 1/2 Ka squared. So 1/2 Ka squared equals 1/2 K delta X squared. And the 1/2 and K is reduced to 1. And so we see that A is equal to really the absolute value of delta X. But what we're proving here is that if I take a mass and here's the relaxed length, here's the equilibrium position, and I take it from there and I pull it down just a tiny bit, and I let, to this spot here, and I let go, it's going to shoot up to some height. And we just showed that that height there is actually the same height above the equilibrium position as it was below. So this thing is going to oscillate back and forth with an amplitude above the equilibrium position, the same as the amplitude below the equilibrium position. We could also pick up the mass, to here and let go, and it would fall to that position. It doesn't matter. So I'm trying to prove to you that this thing oscillates back and forth about the equilibrium position. And I hope that's a little more thorough of a proof for you than this equation being very similar, looking very much the same as this equation here when it was a horizontal spring. One thing, again, you have to be careful of is we're basically here saying that the gravity pulls down on this, right? But it pulls down in such a way to make the oscillation still back and forth the same amount, but not from the equilibrium, or not from the relaxed length of the spring, but about the equilibrium position of the system. So if I were to, kind of draw a graph here of the spring force versus, say, time, I guess. If it were a horizontal spring back over here, and I were to pull this out to this spot and let go, let's call that, I guess that would be in the negative direction. How about if I squish it? Let's just start it and squish it and let go. The force would be to the right with some value of K delta X, but delta X is A. It's really minus A, but the force is positive. And it would go, like this, and it would go down to a minus Ka when you're over here all the way on the right. The force would be to the left. Okay, so it's going to oscillate back and forth, and this is the horizontal spring, or horizontal system, I guess, and it's going to oscillate back and forth. So what would happen now in our case with the vertical spring? Made a little adjustment there so you could see the bottom of this page. So this force of the spring now, it's not going to start at 0. If this spring is already going to be pushing up here, that's going to be our equilibrium position. So it's going to be shifted up to mg. So 0 would be like, if we're going to call up as positive, 0 would be down here somewhere. We don't really care where 0 is, but the point is we're going to oscillate about the mg position. Like that. I didn't draw that graph real great, but you get the idea that there's still an oscillation. It's just not about 0, about the relaxed length of the spring, but about this spot where the force of the spring up equals gravity down. And then I wanted to show you just a little example problem. So what if we wanted to find the change in the potential energy of the spring? So I'm going to keep the same letters here. So I have the spring, its length is L. We're going to pull it down, delta L. And then that's where the spring force up equals gravity down. And then we're going to even displace it farther down, an amplitude A, a distance A. And we already know it goes up a distance A. And we're going to find how much does the spring potential energy change from there. We could do there to there. We could do from here to here. Since we did from there to there before, I'll go from here to here. So this is the final. This is the initial. So this length here that the string is stretched is delta L plus A. So that's going to be my initial delta X. So 1/2 K, and delta X is this delta L plus A. And then my final position is delta L minus A. and this actually should look, very similar to this whole side over here. We had delta L plus A, and delta L, now it's minus A instead of, I just proved that delta X was equal to A. That's what we were doing. So we're just going to basically subtract those numbers. So we get 1/2 K delta L squared minus 2 times 1/2 is 1 K delta L A plus 1/2 K A squared. That's that foiled. And then I'm just going to subtract all of this. 1/2 K delta L squared minus 1/2, forgot the squared, minus 1/2 times 2 is 1 K delta L A, and minus 1/2 K A squared for the last term. So you'll see these cancel out, and we end up with minus 2 K delta L all times A. That's the change in potential energy. Why is it negative? Well, the spring had more potential energy here than it does here, so the spring has lost spring potential energy, elastic potential energy. Now we can do something with this. Where did that spring potential energy go? Well, the mass wasn't moving here at the very bottom, and it's not moving there at the very top where it comes to rest, so it goes into the gravitational potential energy. So we could say if we wanted the change in gravitational potential energy will be positive, it's going to move upward. And the spring potential energy's change will be negative, so we just throw a minus sign on these two guys, is minus 2K delta L times A is positive 2K delta L times A. And all this has to be equal to mg delta y, right? How much it moves up or down is 2K delta L times A. But there's that K delta L again. So this K delta L is also 2 mg times A, because remember, this spot here, where the spring force up equals gravity down, is K delta L, because delta L is delta X, equals mg. I'm going to plug that in again down here. So mg delta y, and of course, mg cancels out. And surprise, surprise, delta y equals 2a, because it goes up a and up another a for a total of 2a. So the change in gravitational potential energy is mg times 2a. I saw a question in the book as well. How many a does something go through when it oscillates, one full oscillation? So this will go a up, and a down is a total distance of 4a. And I suggest as you're going through the book, take a look at the questions that they ask you during the text. What I mean is they ask you stuff here. Let's see if I can find that exact problem. But they ask you things like these quick quiz questions here. And that, here's that one I was just talking about. What total distance does it travel in one full cycle of its motion? The answer is D. And they also, those are quick quizzes. Those answers are in the back. They have other questions they ask you, at the end of problems sometimes. Question 13.2, exercise 13.2. So the exercises have answers here. The questions and the quick quizzes, I believe, have answers in the very back of the book. So what I did was I took a little Post-it note and I just put it back here. So I just grabbed this and flipped to the back to chapter 13. This is page A.66. But here's the quick quizzes. Here's the example questions before you get to the end of the chapter, multiple choice. Conceptual, and problems. Here are the quick quizzes and examples. I would suggest as you go through these, look at those questions. The exercises are probably too long to do, but the quick quizzes are good. Give yourself a little checking for understanding question, multiple choice. You can look it up in the back of the book. Put a little sticky note back there. Just makes it really, really handy and quick to look back at those answers. All right, I know that was longer than I thought, but that's kind of a finishing up 13.2.